go ahead and start.
Of course. So yes, I am the Environmental Affairs Manager. I actually got started with Dunn Edwards as a chemist. So I created the EnduraCat and worked on a few other projects with the actual product development group. I got my background in chemistry. I got my bachelor's for that. And then I got a master's in polymers and coatings from California, San Luis Obispo. Worked under a few professors that I'm going to be mentioning today. So that's really exciting to be able to mention them again and cite them as they were part of my journey. But yeah, so I will leave my contact information on the last slide at the end. So if there's questions after we do a Q&A after the actual presentation that you want to go ahead and then know how to contact me, we can go ahead and do that. I will now go into presentation mode, move all these little screens and items. And also during the presentation, just so that way it's less distracting, I'm going to go ahead and turn my camera off. So we'll just focus on my screen. Okay. So again, hello everybody. Today we're going to be talking about reactivity adjusted volatile organic compound determination, an alternative to the conventional. Let's see. So since the 1970s, VOCs have been regulated in paints and coatings. This was done as part of the United States Clean Air Acts, which were a set of acts beginning in the 1950s with the goal of reducing 5 key pollutants. They were VOCs, carbon monoxide, sulfur dioxide, nitrogen oxides, and particulate matter. VOCs are emitted carbon-based compounds that react with nitrogen oxide and sunlight, meaning UV light and heat, to produce ground-level ozone. And ground-level ozone is known to reduce the size of our stratospheric ozone layer. But paints aren't the only sources of VOCs. We also see them in fabrics and foam, cleaning agents, hairspray, vehicle exhaust, and biophilic sources such as trees contribute as well. And what's interesting is that natural sources of VOC emissions are about 60% of what we see in our normal ground level ozone, and it's only 1% that are actually being contributed from the paints and coatings industry. To give more of a background on the Clean Air Acts and EPA, the first Clean Air Act was enacted in in the 1950s, and it was really the beginning of emission regulation in the US. This 1950s Clean Air Act primarily focused on transportation emissions, and it was in the 1960s that CARB was created, or the California Air Resources Board, to oversee these types of emissions in California. And recognizing a need for a federal regulatory body, the Clean Air Act of 1970 created the EPA to oversee not just air quality, but all environmental matters. And back in the 1970s, most of the coatings were solvent-based. And knowing that the solvents create emissions, the EPA wanted to limit these emissions. And their first step was to hire a private company to investigate how VOCs and coatings should be limited. In 1978, this private company stated that VOCs and non-flats should be 250 grams per liter, but this seriously negatively affected the quality of paint. Essentially, this number wasn't feasible because it was too ahead of its time. And to highlight this, in 1981, non-flat paints in California were still at 450 grams per liter and didn't go below 400 grams per liter until 1987. And it didn't hit 50 grams per liter, the number that we know today, until the year 2000. This shift in lower VOCs took 19 years, and it caused a huge shift in chemical manufacturing, formula and manufacturing processes, application training, and general education across DIYers, professional applicators, and academics. But thankfully, though, there was a lot of back and forth between the government and industry, and from that, we learned that if the limits of VOC aren't realistic, there will be a fiscal and environmental cost associated. Coatings that were forced to have lower VOCs at this time before proper technology was available saw poor performance properties, which meant that more materials were being used and wasted as more paint had to be created and applied. VOC regulation across the US. So all states must follow the EPA Architectural and Industrial Maintenance Rule, or EPA AIM, the federal rule. Some states and regions and even districts can go further in their limitations of VOCs, and products in these areas can only be sold as long as VOC products are compliant. So if you buy a paint in California, you can use it, of course, in California, but if you try to bring in a higher VOC coating into California than the California standards, you will not be able to do so. Here's a map that I actually created as part of my thesis work. So this was done back in 2015, so some of this might not be completely accurate, but the EPA broke down the US into 10 different regions. And some of these regions, like I said, adopted their own air emissions and regulations. For instance, over in the Pacific Southwest in California, we have not only our California Air Resources Board, but we also have the South Coast Air Quality Management District that is known to be the strictest in all of the US. And in Arizona, not only do they follow their standards of the state of Arizona, but Maricopa County follows its own rules. Some regions along the East Coast follow LATICO, which is the Lake Michigan Air Board Consortium, or OTC, which is the Ozone Transport Commission. And they have a few phases as well. And right now, we're seeing shifts in what some states and districts are choosing to follow. Since while the federal AIM limits are easier to follow, there's been so many advances in technology wherein the higher limits aren't really necessary to get the good paint performance. You can also achieve these higher performance properties with lower VOCs. And you'll see products marketed across different regions for different properties. This exists through obviously the performance and the ingredients of the coatings. So for example, here in the Pacific Southwest, since we don't really see blizzards or hurricanes, we might see snowstorms in some areas, and hot weather is a dry heat. We really tailor the ingredients and the actual performance of the coating to meet the weather that we see here. Our buildings are also different in some ways. We utilize a lot of stucco, whereas on the East Coast, there's a lot of brick or masonry. So all these products, and especially when you see regional companies, they really specify on the climate and the building structures that are going to be using those these coatings. Oops. So as stated before, VOC regulation touches a lot of different industries, whether it's vehicle emissions or hairspray or cleaning agents. But one of these affected industries is building requirements, which makes sense. I mean, these coatings have to be used somewhere, and where there are government agencies, there are environmental groups, and where there are environmental groups, there are demands for even stricter regulations and for other industries to adopt such measures. Which leads us to groups that I'm sure you have all dealt with, such as the U.S. Green Building Council, the LEED program, and all of their variations, whether it's 2009, version 4, or version 4.1. And one of the requirements for LEED is that a paint needs to prove its low emitting status. On a manufacturer's end in California, this means that we have to follow the California Department of Public Health's VOC testing through standard practice. And this method is actually called the standard method for the testing and evaluation of volatile organic chemical emissions from indoor sources using environmental chambers, which is quite a mouthful. So most of us just go by a shorter abbreviation and just call it a VOC emission standard or emission report. Another abbreviation that I'm sure you've seen before is CHIPS, which is the Collaborative for High Performance Schools. And they allow for low emitting material criteria for schools, which is section 01350. Either way, these state testings are done through third parties, and they are not done internally from a manufacturer. In other areas that we see requirements for low VOCs is with the National Association of Home Builders Model Green Home Building Guides, and now well building requirements. So how is the testing actually done for these VOCs? Well, federally, and the rule of the land is this federal aim method 24. And this is a determination of VOC content using water content, density, volume solids, and weight solids of a surface coating. And it was really developed for a wide variety of coatings and inks, really good for solvent-bornes. The problem is that with water-based coatings, the higher the water content, the higher the imprecision. And because of this, or the reason for this, I should say, is the method that is actually used. So here we can see an oven, and we see this little aluminum cup. So the method that you use is to take a set volume of your coating and dilute it in water. Take that mass, take the mass of the cup, understanding how much you're actually using of the different materials, and then to put the little cup into the oven. I forget off the top of my head if it's for 1 hour or for 3, but at the end of that time, you take out the cup and you weigh it, and you go ahead and see what that mass difference is. And then again, so using water content and density and things like that, you would be able to find the mass of VOCs within that coating. One problem, however, is that it's not very accurate, like I said, and it's not meant for systems that have low VOCs. So instead of this, there is ASTM D6886. This was created in part by one of my advisors, Dr. Dane Jones from Cal Poly San Luis Obispo, and this uses gas chromatography. And what it does is that you still, again, dilute your paint. You know the amount of paint you're using, you know the amount of the extraction solvent that you're using. You put it into a needle, and you put the needle into the gas chromatography instrument, and that insertion point is incredibly hot. So it is then able to track thermal decomposition tracking. So I show 2 graphs here along with the image of what this actually looks like, where you have your system, your gas chromatography, and then it's connected to a computer. So a little more modern of a method. And here on, I would say then the leftmost example of this slide, we can see what we would normally get. And I apologize if it's cut out where you can't see what the actual X and Y bar graphs are supposed to represent, or the title of that. Hopefully you can see that it says time on the X, and then you can read the Y value. So where it says chloroform and dibromochloromethane, this is what we would see using a gas chromatography. So after a certain amount of time, we would then see a peak, and this peak indicates certain chemicals. And we know this because at one point, through a lot of time and effort, somebody went with these chemicals one by one and figured out where they alluded to and what time they came out at. And what's interesting and troubling is that when you get a paint and you have to figure out what's in your actual product that's creating these VOCs or contributing to VOC content, you would get a graph that looks like what we see on the right. So you have a lot of these lines. You have to figure out at what point do you stop considering a product to be a VOC, and then go in with honestly a huge notebook as your sort of dictionary to go through and figure out what these products actually are. And this is actually great for solvent and waterborne system, and it's good for low VOCs. The only thing it's not suitable for are 2-component systems, mainly because they would then react with each other within the gas chromatography, and that would be a very expensive mistake. So we have these standards and we have these testing methods which give us a number to follow and to keep in mind. And we have the green building standards that further require this particular number. But this number creates a false narrative. When we have a number, say 50, we're thinking that 50 grams per liter of VOCs is worse than 30 grams per liter, which is worse than 0 grams per liter. And all of these are at least better than 100 grams per liter or higher. But that isn't necessarily true. One, we need to consider that different coatings have different purposes, and they can't all have the same amount of VOCs. For example, marine coatings typically have high VOC content, and this is because a ship is sitting in the ocean the whole time, and we need to make sure that that coating is going to last on that metal substrate. Airplane coatings have their own particular regulations, and we need to make sure that frost doesn't build up on any of these airplanes. And what's interesting, fun fact, is that airplanes also have a debugging coating. So the reason why, as you're flying, that the screen or the windshield isn't piled up with a massive amount of bugs is because there's a coating on top of the window to make sure that these bug guts aren't sticking to the window and impeding vision. Moving on, for indoor coatings, we have 50 grams per liter. We have ones that are 0 grams per liter, 0 VOC. But either way, all these numbers, when taken by themselves, assume that there's a huge safety risk associated. That if you choose a 50 grams per liter over one that's 0 grams per liter, that you are willfully inhaling these dangerous compounds and willfully putting people at risk, which isn't really true. There's a lot more to these VOC numbers. And for example, the limitation of the thought of just this number as it is, as a primary indicator of environmental acceptability, is that it does not consider relative reactivity, potential toxicity of the VOCs. Again, VOCs are still chemicals that are in the air and emitted from a chemical, and coating performance overall. So if you see something that has a 0 grams per liter VOC over one that's 50, that's not to say that the performance of either paint is better or worse than each other as a reason of VOC. So that brings us to today's main theme, that VOCs are not all the same. They are compounds that are exempt VOCs, meaning they don't off-gas to create ozone, and there are different reactivities of the VOCs that are released. So if we pay attention to the reactivities of VOCs that are released, we're focusing then on how these VOCs actually react to create ozone, rather than simply assuming that every chemical is the same and has the exact same reactivity, or bringing back to those other points from the previous slide in terms of toxicity or even performance. So therefore, if we focus on having a reactivity-based standards, we're not only regulating VOCs in a better manner, we're also optimizing the use of VOCs for maximum eco-efficiency. So if we see that a VOC has a high reactivity number, then we would want to make sure that we were not using that type of chemical, that we were using something that had a low reactivity, because it's these low reactivities that aren't producing ozone. So by having a realistic measure, again, of what contributes to ozone depletion, we heighten our understanding of efficiency, where an eco-efficiency can be defined as the ability to satisfy human needs in a way that minimizes adverse impacts on energy, material resources, environmental quality, and human health and safety. And I want to focus a second on where I have ability to satisfy human needs. I know this sounds a little odd, especially when most definitions and mentions of being environmental do so with the message that humans are bad, that we are polluting the earth, which is in some parts true, but again, we are all on this earth, and as much of the guilt around being a human is prevalent and heavy, so too is the message about sharing our environment. And for humans, our environment or habitat is that of a built environment. We build our homes and our shelters out of earthly substances, however they're manufactured, and it's our duty to protect and preserve those materials and preserve our habitat. So to be eco-efficient with what we've built already and what we will build, we need a true metric for what we're doing and how we're affecting the safety of all creatures, which is incredibly important in this day and age when we're already teaching every living generation on how to be better. But to be better, we need to be smarter. And that, in our opinion, is through reactivity adjusted VOCs, or RAVOC. So the goal of RAVOC and the goal of this presentation is to show that we can improve our ozone control by considering not just the mass of VOC in a coating, but also considering how those VOCs react or photoreact. So with the reactivity adjusted goal, this would be to allow coatings to fulfill their environmentally beneficial purpose in ways that support optimum air quality improvement, and prevents detriments to the environmental and human health. Again, just taking the consideration of humans are meant to be in this environment and that we need to then just do something a little bit better, a little bit smarter on how to actually preserve it. So before we go into actually testing for RAVOC specifically and how it can be used for manufacturers to improve and to educate people, I want to go into the history of RAVOC because it isn't a new theory. It's just one that's sort of been pushed to the back burner. So here we have NARSTO, and NARSTO is a North American research strategy for tropospheric ozone, and it was a public and private partnership with NARSTO of industry sponsors such as ASCO-Nobel, Bayer Process Corporation, Benjamin Moore, Dunn Edwards, Eastman Chemical, PPG, Rome and Haas, Sherwin-Williams, and Valspar, and government agencies such as the South Coast Air Quality Management District. And they published a report in 2005 evaluating the strengths and weaknesses of North American emission inventories and made recommendations for improving their effectiveness. The theme within the report was that there was a need for increased coordination among the stakeholders, so government, manufacturers, academics, which is still a theme today, that we all need to coordinate and collaborate on this path forward. So from this NARSTO report, there has been an increase in inventory emissions. So for example, manufacturers are required to report on VOC emissions to the state every year. But there's much more that needs to be done back from the early 2000s, back when this report was published, that needs to happen today as well. And these include accurate emission estimation methods and analysis, improving awareness over true emission sources, and eventually accurate regulations. And all these recommendations directly point to adopting RAVOC as a standard for reporting VOCs and implementing rules based on information gained from analyzing RAVOC values. And I really recommend reading this follow-up report done in 2019 that shows, based on the 8 recommendations of NARSTO, where we are today. And this image might be a little difficult, so I went ahead and just made its own slide for it. So there's 8 parts to this NARSTO document, and we can see that everything is circular. So everything should still be a continual process. There is no limit to the education. There's no limit to stopping, evaluating these materials and continuing the science behind it. But still, we have our initial data collection, measurement methods, field tests and sampling, looking at emission factors and modeling. And we go forward with the rest of these points into having a preliminary emission inventory calculation. And these should be reviewed by the states and other stakeholders, such as manufacturers, and look at the locality of where you are and what that actually means. So there's going to be different levels of nitrogen oxide that's present in the atmosphere in different areas. So that needs to be considered and modeled and factored for. Same as you could think of for in LA, we have a lot of smog. If you go over to the Midwest, you're not going to have that same amount of smog. So that theme of considering of where you're at and then basing your manufacturing off of that. So after that, we have an improved emission inventory that can then go into applications or end products. We could then actually start modeling these things in a better way to actually see how these changes, once implemented, would be affecting our air quality. So definitely recommend reading this. Just to continue with RAVOC history, The UC Riverside College of Engineering's Center for Environmental Research and Technology, or CECERT for short, evaluates a wide scope of VOC emission sources. Dr. Joseph Norbeck, a CECERT director, researched and published information showcasing in 2003 how cars in 2010 could meet federal smog standards by 2010 with his study of extremely low emission vehicles. By targeting RAVOC values, there was a clear path on what to focus on within gasoline and how to build EV vehicles, which would then allow us to meet a 2010 standard. And part of this is being seen today with net zero and the push to EV vehicles, but there's still no focus on RAVOC. And in that same year of 2003, William P. L. Carter, who was a research chemist, created a detailed atmospheric chemical mechanism for RAVOC and NOx, or NOx, or nitrous oxide, using a method named SAPRC-99, which was an update to the SAPRC-90, and this was to more accurately determine the reactivities of more than 400 types of VOCs. And the mechanism was then able to test for and against ozone reactivity predictions for over 80 types of VOCs. And the update to the -90 method was based on using MIRs, or maximum incremental reactivity. And MIR values tell us how much ground level ozone can potentially be formed in the worst case scenario. So by that, I mean the highest amount of nitrous oxide that you could reasonably consider in an area. And William P. L. Carter found the MIR values of chemicals by putting VOCs in different NOx environments to actually see the reactivity. And I do want to note that MIR values are accepted by CARB and the US EPA, and both agencies actually use MIRs for aerosol coatings, but not for architectural coatings at this time. So how do we actually move forward with this perspective of needing to advance our knowledge of RAVOC as a metric for what goes into our paint products? There's five overall steps that we can look at. We can investigate scientific issues relating to eco-efficiency, so the metrics of how improvements can actually affect our current assumptions and modeling of ozone formation. We can create coatings based on these predictions and with ingredients known to have low reactivity. Then we would substantiate our claims of the RAVOC as being the best way of measuring VOCs by evaluating the performance of our coatings and the life cycle. And then once we know the coatings are viable, we can participate in the development of new eco-efficient regulatory standards and even voluntary standards such as building standards. And lastly, we can continue to innovate and improve to maximize our ingredients for optimal eco-efficiency. So again, once we know the ingredients that have those high MIR values or those high RAVOC values that are contributing to ozone formation, we could then focus on not using those and only using chemicals that are known to have low reactivity. So here is the RAVOC calculation. So RAVOC is VOC times RAF, where an RAF is a reactivity adjustment factor. And we have this pretty little equation that then tells us how exactly to calculate it further. But to be honest, we do have a RAVOC calculator spreadsheet to calculate the RAVOC content and VOC content for the entire formula, which is super easy and helpful. So I'm talking about VOCs, I'm talking about RAVOC, but how is it actually used and where do we actually see this? At Dunn Edwards, for several years, we have been showcasing our own little RAVOC rated number. So we have our own little icon on this that we put on all of our products, and along all of our PDSs, we will actually state the maximum VOC content and the maximum RAVOC content. And we do the same thing on our labels. So we can see, for example, here, where the maximum VOC content of our new exquisite product, which is an excellent interior matte. This product, by normal standards, has 50 grams per liter of VOC emissions. However, it's only 15 grams per liter of that number that is actually reacting to create ozone. So again, this shows the distinction of, you see one number, you automatically assume that there might be a health risk associated, that there might be a benefit over using 0 grams per liter in this situation because of an assumed health benefit. But then we go ahead and we can see, well, what is the actual content of this? What is it actually telling us? And this is an example where, moving forward, if we start using this RAVOC as itself, then we can go ahead and really educate and really focus on what we're doing. So when we turn in these values to the state of what our VOC content is, and we use 50 grams per liter, imagine we are one company and everybody else that's having to do the same thing, they are then overestimating on those VOC contents. So now all of our estimations for all of our contents are widely exaggerated. So the advantage of RAVOC. Again, it provides meaningful information. It avoids misimpression that products contain or release ozone directly. It can be applied across multiple domains. So as I stated before, we don't see VOCs just from paints and coatings. They're from consumer products, whether it's from toys or from fabric or from furniture, hairspray, the like. We can use this across a lot of different areas. It's also easily calculated, even for entire formula sets, and it provides a clear path for how we can improve our products in the future. Again, by actually knowing what's in our products and knowing what's going on, we can formulate around that to have a better outcome and to really understand what's going on in our atmosphere and to better prepare for how to improve our atmosphere. So in summary, VOC regulations were a great start to limit the amount of solvents used in coatings, and it paved the way for a societal focus on improving air quality. The methods for testing VOCs may give varying results. VOCs may be believed to be ozone itself rather than chemicals that react to create ozone. There is a disconnect between what VOCs are and a lack of awareness that not all VOCs are equal. And RAVOC, or reactivity adjusted VOCs, proves that not all VOCs are equal and should be the standard for VOC content ratings moving forward. And by focusing on the reactivity of emissions, we can better protect our environment. And I want to take a quick moment to go through this, our Dunn-Edwards website, our environmental website. And here we see, this is just some content about Dunn-Edwards and how we are greener by design. But at the bottom, you scroll through and we see our RAVOC button, along with an explanation of what RAVOC is, how we've adopted it, the history of it. It goes into what does a 0 VOC mean, what does low versus ultra low VOC mean, discussions about VOCs, whether they're toxic or not, and of course, how do RAVOC ratings work and are they required? So I definitely recommend going to our Dunn-Edwards website. We are currently in the process of updating this, so where you can find our environmental page is down here in the About Us section where it says Environment. So going back, I want to thank everybody. I know that some of you had some difficulties logging on. I am happy to have you here today. This is my contact information along with the website that, again, you can find that environmental link. If you have any questions, please do not hesitate to go ahead and email me. I see now I do not have my email up, so I will be updating that and putting it in the chat. But at this point, if I'm going to turn on my camera, and if anyone wants to have their questions answered, go ahead and we can do that.